2013's polar vortex, 1816's year without a summer, an ice age that lasted millions of years. None of that compares to the longest winter Earth ever saw, one that stretched on for 300 million years. What caused it? And could it happen again? The first signs of life on Earth appeared 3.5 billion years ago. Well, single-celled microbes that lived in the ocean, to be specific. Tiny and microscopic, they didn't seem like much, but these organisms were about to change the whole world. And by the time this chain reaction finished, Earth would be unrecognizable. The planet these life forms evolved on looked nothing like the Earth today. Most continents didn't exist yet, and the land wasn't even visible. Sea levels were so high that scientists think land first rose above the ocean 3.7 billion years ago, just 200 million years before the first traces of life appeared. And how can they know that? A 3.2 billion year old slab of ocean crust held the clue. Its chemistry revealed the truth. Seawater covered almost everything. Earth was a real-life water world. If you're imagining a planet covered in sparkling blue ocean waves, don't. In fact, if you were there, you wouldn't be imagining anything. You would die instantly, thanks to the near-total lack of oxygen. The oceans were vast, endless, and tinged green. The severe lack of oxygen in the air led to a lot of metallic iron dissolving in the water. Just one big, greenish, rusty ocean with an occasional speck of land thrown in somewhere. And that land would have been barren and rocky. No grass, no plants, no sand. Well, how about the air? Is that any better? Well, it was orange. It looked like a filter had been slapped on it. Being on land was a non-starter as well. The UV radiation from the sun would have fried anything on the spot. And that was just the start. The planet was also really unstable. Geologists have found evidence of huge, near-constant volcanic eruptions all over the world. The planet was still young and its center was much hotter than it is today. There was basically a Pompeii-level event happening every week, mostly underwater. Unsurprisingly, there wasn't any real complex life yet. If columns of lava erupting out of the green ocean into the orange sky weren't enough, the atmosphere was chock full of methane and carbon dioxide, but particularly methane. Back then, carbon dioxide was present in the atmosphere at 10 to 2,500 times its current level. Methane was 10,000 times higher than it is now, and like we said, you could forget about oxygen. But somehow life found a way. Single-celled organisms began to appear in the oceans, in deep-sea hydrothermal vents, or in shallow water, maybe even both. Scientists still don't agree on what sparked that first explosion of life. One theory is that constant lightning in Earth's violent early atmosphere turned methane and nitrogen into amino acids, the building blocks of life. Another is that those building blocks arrived from space, delivered by the comets and the meteorites that bombarded early Earth. Either way, Earth's stormy atmosphere became a chemistry lab. Reactions in the air and the ocean started producing amino acids and sugars. Over time, those ingredients formed more complex molecules, including RNA. And then came the next leap: RNA trapped inside fatty lipid bubbles, not life as we know it, but the most basic version of it. And since the air was a suffocating mix of methane and carbon dioxide, those tiny life forms survived the only way they could: by feeding on those gases. One evolving line of these microbes, cyanobacteria, started producing something else after absorbing the methane: oxygen. So much so that 2.5 billion years ago, the Great Oxidation Event happened. But while that might sound good, it actually made things worse. And that wasn't the real danger. Oxygen buildup and eliminating of carbon dioxide caused a complete ecological disaster billions of years ago. Think of methane as a huge blanket wrapped around the Earth. As oxygen built up, levels of methane went down. The oxygen also reacted with the methane in the atmosphere to produce carbon dioxide and water. That extra carbon dioxide was easier for ocean microbes to consume than the methane, so they burned through it fast. And as they did, they pumped out more oxygen, accelerating the planet's oxygenation and sending temperatures crashing. All of that oxygen started polluting the planet because for life back then, oxygen was toxic. The scary part? None of this looked like a disaster yet, but the planet was already sliding into it. At the same time that all this was happening, the supercontinent Kenorland was breaking apart, and that is where everything goes wrong. That's right, there were supercontinents before Pangaea. Kenorland was probably smaller than what you would picture, since so much of early Earth was still underwater, but it may have been the planet's first true supercontinent, forming around 2.7 billion years ago. The baby continent comprised of most of the US and Canada, Greenland, Scandinavia, Western Australia, and part of the Kalahari Desert. Scientists think that it was most likely centered around the equator. For the first 100 million years of its existence, if not longer, it was by far the world's most dominant landmass. Experts have suggested the presence of another smaller continent called the southern supercontinent, but others push back on that theory, saying there's not enough evidence backing it up. However, what is certain is that Kenorland dominated the globe, with other strips of land being few and far between. Geologists believe Kenorland started breaking up between 2.6 and 2.5 billion years ago, right before the Huronian Ice Age, and they don't think that's a coincidence, because the planet was about to tip, and it wouldn't tip back for 300 million years. But how does a continent breaking up create an ice age? First of all, as a continent breaks up, it means more land finds itself closer to the ocean. Moist air from the sea can then cover more land overall, increasing cloud formation over formerly dry interiors and causing more rain. The shallower seas created by the continent breakups also warm up faster. The warmer, shallower water evaporates much more easily, increasing the moisture in the atmosphere. All of this created way more rainfall than ever existed before, and that rain helped bring about an endless winter. But that's not what made it catastrophic. When a continent breaks apart, it's like smashing a rock into pieces. You suddenly get way more surface area exposed to the elements. And on early Earth, a lot of that land was made up of volcanic basalt, which weathers fast. Now add a carbon dioxide-heavy atmosphere, and that meant acid rain, and acid rain chews through basalt even faster. As the rock broke down, the rain pulled carbon dioxide out of the air, and it locked it up into the ground, or it washed it into the oceans through runoff. The land and the sea became one massive carbon sink, and that meant the planet was losing carbon dioxide faster than it could make it. And once this starts, how do you stop it? Couple that with the fact that the sun was anywhere between 6 to 15% weaker than it is today, so there wasn't enough warmth counteracting the fast drawdown of carbon dioxide and rapid chilling of the planet. Every possible factor came together to pump the Earth full of oxygen while taking all of its CO2 out. This had the effect of kicking the Earth out of a warm landscape into a frozen tundra. And then Earth crossed the line. Over a period of around 100 million years, the world entered the Huronian Ice Age, and this is where Earth's long winter begins. Polar ice, which had not been seen before, started to form at the caps and then work its way down to the equator. Scientists found evidence that at some point the ice extended all the way to the equator at sea level, meaning that Earth might have been pretty much frozen solid. As the ice spread, sea levels dropped, and more land rose into view. At the same time, Earth was still in its early growing pain stage, with new crust forming and reshaping the surface. One model estimates the planet went from almost entirely ocean-covered to nearly 20% land. Still, that is nowhere near modern Earth. Today, land makes up just under 30% of the planet's surface. Scientists also disagree on whether the seas were fully frozen over or just kinda slushy in parts. But they agree that at multiple points during the Huronian Ice Age, the planet was practically turned into a giant snowball. While it's hard to gauge the exact temperature of the Earth, literally billions of years ago, one model suggests the average global temperature during the Huronian Ice Age was negative 45.4 degrees Fahrenheit. By comparison, the 20th century average temperature of the Earth was a much more comfortable 57 degrees Fahrenheit. The ice killed off a lot of the organisms that had been fighting for their single-celled lives. Those didn't die from the freezing cold, they died from oxygen poisoning, due to the lack of methane freely floating around the atmosphere. But some survived, specifically those that adapted to the oxygen now swarming the planet. Some even evolved to use the ever-present oxygen for survival. Strangely enough, even though the Huronian Ice Age killed off a huge chunk of life on Earth at the time, it was absolutely crucial for life on Earth as we know it today. It caused what evolutionary biologists call a population bottleneck, followed by a founder flush event. A population bottleneck is simple. Some event causes most of everything living to be killed off. The founder flush event meant that the few remaining organisms become founders of every form of life that comes after them, since most of their competition has been flushed out by whatever crazy disaster just happened. The extinction of most old anaerobic life forms on Earth changed the face of the planet as we know it, because it led to a rapid spread of aerobic or oxygen-using organisms, and humans would eventually evolve from those first tiny oxygen-sucking microbes, something that probably would have never happened with anaerobic organisms. It turns out evolving to take in oxygen instead of methane was a huge win for life in general. Organisms became bigger and more diverse at a faster pace than ever before. Oxygen is much better at generating energy after an organism breaks down its nutrients. That's because of its high redox potential, which basically means it is great at accepting electrons and creating a lot more energy for aerobic organisms than methane ever could for its microbes. Scientists believe that this is what eventually allowed the development of multicellular organisms, then organisms that made their way onto the land, and the absolute massive circus of life forms that we find on Earth and in the oceans today. And it's all thanks to a mass of cyanobacteria overwhelming the planet with oxygen. They even produced an extra perk. Oxygen led to the creation of the ozone layer, which is absolutely essential for shielding us from the sun's UV radiation. Without the ozone layer, experts don't think that we would have made it onto the land. The sun's rays were too powerful and dangerous to let organisms survive on land before that. That's why the first life on Earth wanted at least a few feet of sea between them and the giant yellow ball in the sky. So the icy winter that started forming between 2.5 to 2.4 billion years ago was almost a welcome change. Once it fully had its hold on the world at that 2.4 billion year mark, it enveloped everything. The Earth would be covered in snow and ice for the next 300 million years. And when we say 300 million years, we are not exaggerating. This wasn't just a bad winter. It wasn't even an ice age in the way we normally imagine it. This was the kind of cold that outlasts entire eras of life. A winter so long the continents could have drifted and the ice would have still been there. And once it started, it basically couldn't stop itself. But the ice wasn't static, it ebbed and it flowed. Ancient rocks, like those in Canada's Huronian supergroup, show evidence of different glacial layers. This means the glaciers advanced, retreated, advanced, and retreated again and again during the Ice Age. Scientists think that was because warming and cooling influenced cyanobacteria's activity. When it got warm, cyanobacteria produced more oxygen, removing methane from the atmosphere and making the temperature plummet. The colder it got, the more cyanobacteria slowed down their activity. This would let the volcanic activity and other processes build up more greenhouse gases in the atmosphere, making the Earth warm up all over again, and then the cycle would start over one more time. But this didn't happen from one day to the next, or even one century to the next. Each warming and cooling period took millions of years. That is, until the glaciers disappeared altogether, because the planet wasn't done changing yet. The microbes that caused the Ice Age also brought about its end. Since the old anaerobic methane-eating organisms had been annihilated, the new aerobic ones quickly filled in the gaps left behind. And aside from all the cyanobacteria, the rest were absolutely feasting on oxygen and producing carbon dioxide. The more CO2 built up in the atmosphere, the warmer the planet got, until it eventually became so warm that the glaciers melted for good. Right after the thaw, Earth wouldn't have looked peaceful, it would have looked violent. Imagine miles of ice collapsing, dumping oceans of meltwater across rock that hadn't seen the sky in hundreds of millions of years. Sea levels would surge, coastlines would redraw themselves, and the air would fill with fog and relentless storms as heat and water slammed back into the system all at once. It was a planet going from deep freeze to flood almost overnight, at least by Earth standards. The planet basically entered a billion-year-long sauna age, at least compared to what had come before. Another ice age wouldn't come around until the Cryogenian, which started 850 million years ago, 1.25 billion years after the Huronian Ice Age ended. The Cryogenian period lasted 215 million years, handing the Huronian Ice Age an easy win for the worst ice age ever, at least so far. But we'll get to that soon. The long-term positive effects on the development of life on this planet are just one of the many ways the Huronian Ice Age influenced our modern world. Without it, Noah's Ark might have just been the story of Noah taking a bunch of microbe pairs onto a ship to save them from a flood. But the flood would just be the constant state of the world, and Noah, or stories in general, wouldn't exist. The breakup of Kenorland around that time also caused plate tectonics as we know them to develop. A primitive version of them already existed, but with these smaller land masses moving around, clashing into others, and shifting, the plate movements came much closer to what they're like today. This not only developed our current continents, the land you are standing on right now, but also our current hydrological cycle, one much more intense than the one that existed in Earth's infancy. This cycle, which efficiently moves water through our Earth and atmosphere, allows life to flourish and generally moderates the climate alongside the planet's current diversity of species. But now we're dumping carbon dioxide into the atmosphere, and this time it's cows that are pumping methane right back out. So here's the question: could anything like the Huronian Ice Age ever happen again? There is kind of a good news, bad news scenario here. The good news is that Earth hasn't seen anything even close to ice ages that long or that brutal in the last 500 million years. After all, the planet is much more stable than it used to be. And there is a greater variety of life on Earth, making sure the entire planet doesn't boil down to a Thunderdome-style match between methane-absorbing and oxygen-absorbing microbes. Plants take in carbon dioxide and release oxygen, while animals take in oxygen and breathe out carbon dioxide. And there's a lot of both types of life forms, leading to a nice balance overall. As geologist Dr. Joseph Meert says, a professor at the University of Florida, "I don't think you can say that we're ever going to see this again." At the same time, we've shown that the breakup of continents into smaller pieces does influence global temperature and results in significant drawdown of carbon dioxide. The bad news is there's a lot of humans around right now, with a lot of unprecedented technology and processes pumping tons of greenhouse gases into the atmosphere at a rate that has never happened before in recorded history. So while it doesn't seem like the next Huronian Ice Age will happen tomorrow, we could be setting off a rapid chain reaction of events that will change the face of our planet as we know it without even realizing it. Also, since compared to single-cell microbes, it is significantly harder for humans to just switch from breathing oxygen to breathing methane or carbon dioxide, it's probably good to stop messing with the atmosphere's makeup of gases if we can help it. Now go check out How Did Humans Sleep During the Ice Age Without Freezing to Death, or click on this video instead.